Great. Well, good afternoon, everyone. Sorry we're a few minutes late starting. My name's James Wilson. I'm Director of Science Policy here at the Royal Society. And it's a great pleasure to welcome you all here this afternoon for this event, which we're very pleased to be hosting in partnership with the Zoological Society of London and the International Programme on the State of the Oceans. We're particularly pleased to be welcoming Charlie Veron to be the keynote speaker this afternoon, and also Sir David Attenborough, who's going to introduce Charlie in just a moment. All I wanted to say before that was, again, welcome, and also just to emphasise from the Royal Society's perspective quite how important this debate, these issues are, particularly at the moment. And we're sitting here today, I think 4 months exactly before the start of the Copenhagen talks in December, when around 10,000 policymakers, environmentalists, scientists and others will be gathering, we hope, to bring the world towards the next stage of a global deal. Within that context, issues of ocean acidification haven't, up to now, had the importance that many people feel they should have done. We here produced a report on this back in 2005, and most recently, just a month or so ago, we and 70 science academies around the world signed a joint statement on ocean acidification, attempting again to draw policymakers' attention to the critical importance of this issue in the context of the Copenhagen talks. So it's very important. It's great to have everyone here. We're very pleased that the meeting this morning has reached some consensus on a statement, which I think you'll hear more about in a moment. But now it gives me great pleasure to hand over to Sir David Attenborough.
Thank you. I guess we all think we know about coral reefs. We've seen it on the telly. And we know very well that they're full of wonder and beauty and astonishment. And of course, we're quite right. That's true. But perhaps in between luxuriating and sitting in the comfort of our chairs and looking at those memorable, unforgettable scenes, we might not be paying enough regard to the other thing about coral reefs, which is that they are key to the health of the oceans. The complexity of the ecological web in the ocean is enormous and still uncharted. But one thing you know for sure is that the coral reef not only demonstrates the multiplicity and biodiversity of the oceans, but also demonstrates the ocean's fragility and the ease with which it can be damaged. Charlie Veron, I can't have nerve for me to call him Charlie Veron. It's a JEN, there's no C there. Charlie Veron is known as Charlie Veron because he knew when he was a boy, they called him Mr. Darwin because of his obsession with the natural world, something which a lot of us, I think, perhaps can feel about. But we are singularly fortunate, for he is one of the great authorities in the world on coral. Indeed, he has identified, discovered, and described about a third of the coral species that we know. He has produced the definitive works, catalogues of the corals of the world. He has, or had, as he himself will say, one of the best jobs in the world, in that he spent his time swimming over the reefs, looking at that marvelous, complex, wonderful landscape and researching new things. What he discovered, of course, was that coral reefs were dying and that he felt it impelled to give up that, as he termed it, cushy job and actually devote himself to looking after and raising awareness about the dangers that are affecting these reefs. There are dangers which will afflict this planet. Things are going to certainly get worse. And the question is, how much can we do to prevent them getting even worse? A lot of us in the media go on about this sort of thing, and we're talking second-hand, if not third-hand or fourth-hand. We're privileged this afternoon to hear about coral reefs first-hand and authoritatively. Charlie Veron. Thank you.
Well, as you can imagine, what a privilege and a pleasure it is to be introduced by, by David. This is not going to be a happy talk because I can tell you right now the answer to that question is yes. If we could lower the lights perhaps of the auditorium, and so I'll be using PowerPoint a lot. I will refer to two things a lot. One is carbon dioxide, obviously, and I will be talking about time. Time is such an important factor in all of this. But first of all, coral reefs are unique, and that's an overused word, I know, but in the real sense, coral reefs are unique on this planet. Firstly, because they exist at the interface of atmosphere and the land. And that's a very physical and chemically stressful place. Not many things would like to live where that coral reef is or live on it. But that place provides corals with everything they need because they live on nothing more than air and water and sunlight. Combine those three and coral reefs can exist. Also, uniquely on this earth, coral reefs are geological structures, yet they're made by living things, yet they are alive. So both geology and biology claim ownership of coral reefs. Not surprisingly, coral reefs are very closely attuned to this very competitive and hostile environment. They are dependent on light in just the same manner as trees are. Without light, they can't exist. And they're very, very fussy about temperature. For the reason of competition, the higher they can get their temperature, the nearer to the temperature limit the ocean offers them, the more competitive they are. Around the Great Barrier Reef, it's 31 degrees. It varies a little bit here and there, but basically corals have got an optimum temperature where they actually work best. And also because they're in the oceans, they are clearly very dependent on the chemistry of the oceans, especially the carbonate chemistry of the oceans. Now, what is so special about coral reefs and so unusual about coral reefs are they are truly nature's historians. That photograph there, you can see the layers are going up the slope there. That's the Huon Peninsula, where those reefs have been studied very, very extensively as they form steps going up the side of a rising landform. They're only a few 100,000 years old, but we can go back a few 100 million years, and we can still find huge survivors of coral reefs today. Some of the fossils that coral reefs form, and they form more fossils than anything else does, are recognizable today. We can still see today's analog, for example, of that fossil. But some are literally hundreds of millions of years old and long extinct. Now, these all tell a story. Whether you have a living coral or a fossil coral, you can cut it, you can find these growth layers, much like the growth layers of trees, which tell how fast the coral grew and when it grew, but it also, in those layers, because they're made of limestone, they preserve the information, the environmental signals that was laid down when those layers formed. So every coral is really a book that really is waiting to be read about the environment that existed when it lived. And so coral reefs are recorders of ancient fauna, and their fossils have the fossils of everything crowded within them, and they are recorders of the physical environment in which they lived in ancient times and in modern times. So go and get a living coral today, slice it up, and you can go back a few hundred years and reconstruct a lot of the environment in which it existed. So with that background of introduction to corals, today's subjects are, not surprisingly, great mass extinction events, because coral reefs have always been implicated tremendously in mass extinction events. In other words, being historians, they've tracked mass extinction events very closely, more than anything else does. And as David mentioned, they are intimately related to the carbon cycle. They are dependent on the carbon cycle, the great matter cycle on Earth. And so any cause of a great mass extinction, you have to look very closely at the carbon cycle. And then we will go on to the events of during our own era, and again back to carbon dioxide, and we will talk about temperature, of course, and we also have a look at sea level change, because sea level change is very dramatic. It is the result of climate, and it is very visible. In fact, it's one of the sources of a lot of misunderstanding about today's climate change. We will talk about the blighting of coral reefs over the last 20 or 30 years by mass bleaching, mass death of reefs due to temperature. We will talk about ocean acidification, the great big gorilla in the cupboard waiting us just down the road. And then, if you're not thoroughly depressed by all that, we will talk about the future. It is not a happy talk. I'm sorry about that. I have been giving talks about coral reefs for a very long time, and usually they are fun talks to give. This one won't be, but I've never given a more important talk in my life. One thing to know about reefs is because they live in such a precarious position on the planet, they are prone to boom and bust cycles. So that if you had a camera mounted up in space and you looked at Earth, and that was a time-lapse camera over millions of years, you would see reefs form and disappear, form and disappear, form and disappear, all according to climate cycles. And so they record those climate cycles with great accuracy. And just to give a quick run-through of reefs and mass extinctions, that is the time span of the life of coral reefs, which is most of the lifespan of the complex life forms that we really recognize today. First reefs were not really reefs, but they were formed of strange tubular things, and we can pass on from there. They soon got displaced by what really are corals, and most of those things in that picture are corals. Then everything went extinct. Almost everything went extinct. Coral stopped growing worldwide over. Reefs stopped forming. Marine life collapsed. There wasn't much terrestrial life, so it was a very much marine event. And that was the first great mass extinction on the Earth, as recorded primarily by coral reefs. But they recovered, and boy did they recover in a big way. Most of the reefs from so long ago are long since gone, but some have been lifted up out of the water, and we see there a huge reef that lived once so long ago, over 400 million years ago. And indeed, these reefs are fairly common in the far northern hemisphere, scattered around the Devonian reefs. And that's a particularly spectacular one. It makes a good climb up to the top in northwest Australia. Now, this reef and so many others around the world suddenly stopped growing. Something happened. The climate that had nurtured them for millions of years turned hostile, and we have the second great mass extinction event. That's the life of a coral reef. But when we get on to the greatest of all mass extinction events, the event that has been known since the 18th century as being the end of the Paleozoic era, coral reefs really copped it, so much so, almost everything went extinct. Every coral on this planet went extinct. No corals that grew in the Paleozoic are now alive or lived through that extinction event. And so we had a new group of corals evolving after that called the Scleractinia, and that's the start of modern corals. And they're fairly different from their predecessors, and they look more or less like that. But they really got their act together because they live in this unique environmental position on this planet, and they started building again gigantic reefs, again, most of which have disappeared, but we still have some remnants. Excuse me. And guess what? They were hit by another mass extinction event And again, the corals were wiped out, almost totally wiped out. And just a few lived on, a very small proportion of the diversity lived on. Evolution kicked in, and we have some of the grandest coral reef remains today. That's the calcareous Alps of Austria, which are huge, as you would know, skiing slopes now. They're coral reefs that formed during the Jurassic Era, and we're right into the time of the dinosaurs now. That's right. At the end of the Mesozoic Era, we had another catastrophe that brought the end of the dinosaurs, a catastrophe which has been studied more than any other geological event on this planet. The KT mass extinction, the end of the Cretaceous mass extinction. Excuse me. You have to forgive my voice, I've been talking all morning. So widely blamed on an asteroid that hit the Gulf of Mexico. Coral reefs then clobbered again, rare, out of existence almost, and today's corals had to reinvent themselves, and they did, and they reinvented themselves. They continued to increase in diversity to modern reefs that we see everywhere today as pretty pictures everywhere. Okay, that is the history of mass extinctions, and is a history very much written by coral reefs because they have such an intricate relationship with the carbon cycle. Carbon dioxide. You may have seen lots of reconstructions of carbon dioxide over the past. This is mine. Not so much accurate than anybody else's, I very much doubt, because it's not accurately portrayed by anybody. The question marks are very big question marks. The dotted lines are rough. The solid lines are, pretty much okay. And what we see is huge changes in carbon dioxide in the atmosphere over this huge amounts of time. Now, carbon dioxide didn't actually follow that path. It zigzagged up and down, up and down, up and down, very, very quickly. But these are the records that have been taken, most of them at a time when the importance of those records was not appreciated. And these are the mass extinction events. And on a finer scale, not on this scale, but on a finer scale, 4 of those 5 mass extinctions correspond with a very, very steep decline in a build-up of carbon dioxide. So a steep increase in the build-up of carbon dioxide. This one was a very sudden decline of carbon dioxide, which can have similar effects on the oceans. This one, perhaps due to the evolution of vascular plants, we don't know. But over the literally 800 years of interest and research and books and monographs and ideas, people have had their ideas about how mass extinctions came about, what drove the Earth to such a catastrophic state where life came down to on its knees. So we're going to look very briefly at the causes of mass extinctions. Firstly, causes that are independent of the carbon cycle, and then those causes that are linked to the carbon cycle. And for those of you who are not too familiar with the carbon cycle, you are part of the carbon cycle because you are largely carbon. So is this building, so are rocks, so are trees. The carbon cycle is the great matter cycle on Earth. And the one really important thing about the carbon cycle is its fast-acting currency is carbon dioxide. Carbon dioxide gets carbon from one form to another quickly and in bulk. It always has. So, listing other people's causes of the mass extinctions, we can start with that asteroid that hit the Gulf of Mexico. Did that cause the demise of the dinosaurs? Many people think so. Many people have thought so. And literally hundreds of books have been written on this subject. Almost certainly not. It certainly didn't do them any good, but it didn't wipe out the dinosaurs and leave frogs croaking beside the creek as happy as can be. And a lot of other things where the timeline is wrong. Did a nuclear winter, like from the result of an asteroid impact or a mega super volcano, cause mass extinctions? Sea level changes, low temperature, high temperature, diseases, toxins. extraterrestrial events, I don't mean Martians, I mean cosmic rays, supernovas and so on, they've all been suggested as causes of one of the mass extinctions or another, and really the asteroid impact would have had a great effect on the last mass extinction, but on none of the others, and all of these can be categorically ruled out for one reason or another. Even high temperature, I do point out, can be ruled out as a cause of mass extinction. So, things that are not ruled out are acid rain, hydrogen sulfide, and so on down that list. Acid rain is being put out quite a number of times. No way, there's not enough acid on this planet. Hydrogen sulfide, well, that's not part of the carbon cycle, it's got no carbon in it, but when anything goes rotten, as you might know, rotten egg gas, you can smell it, and when the oceans are really gone off during times of mass extinctions, hydrogen sulfide has left its trace. So it's there as a culprit. Ocean anoxia, when the oceans ran out of oxygen and became, in effect, dead, certainly. Methane. Well, methane is one of the nasties of today, one of the wild cards that we're facing with today's climate change, and methane may have had this role throughout hundreds of millions of years. It's not on its own enough to cause a mass extinction, but it can sure help. Carbon dioxide is virtually obviously involved in mass extinctions, and so is ocean acidification, which you get when you've got enough carbon dioxide. So we've got mass extinctions, the causes of them linked together, and that is, I guess, a quick run-through of the worst-case scenario that we face today as recorded by coral reefs. So today's subjects, we're going to move on to our own era when there were no mass extinctions. And again, of course, we're going to talk about carbon dioxide. And we know about temperature. We must go into the effects of temperature and sea level changes, because sea level changes, as I mentioned, do depict so clearly the climate changes and the effects of climate changes on the oceans. A reminder only about our last era, the Cenozoic Era. It's tacked on the end, and it's spread over 65 million years from the time of the end of the dinosaurs to today. And there is the Gulf of Mexico with the site where the asteroid, the bolide, hit. Okay, that graph of carbon dioxide now is known in quite a lot more detail. And again, these are not particularly accurate, perhaps, for those specialists in one field or another that are here now, but it's pretty close to it. We have the peaks of carbon dioxide at the KT mass extinctions, right up there at the top. And then we have another peak, as much to do with methane, perhaps, as carbon dioxide, at the late Paleocene thermal maximum, as it's so often called, or the Paleocene-Eocene thermal maximum. And that caused a massive extinction in coral reefs, but not everything else, so it's not a mass extinction. And we had another extinction, a really serious extinction in coral reefs in the Mideocene, again, correlating very closely with carbon dioxide levels. So carbon dioxide levels are very much associated with reef formation. It's about then that, I think at any rate, the Great Barrier Reef started. In one form or another, excuse me, at one form or another along the Queensland coast. But these are great, big time intervals. What we need to do now is to move right to the right-hand side now, in a micron-thick line on that right-hand side, representing the last 500,000 years or so. Now, that is particularly well recorded, not by coral reefs, but by ice cores. When ice is extracted from deep, 2 or 3 kilometre deep cores in Antarctica, in glaciers, in Greenland, and the ice is crushed, the carbon dioxide is extracted, and that is what they show. They show the glacial cycles being well correlated with levels of carbon dioxide. And here we are today, right up there. We're way up above the glacial cycles of carbon dioxide. And in fact, if you want to plot the temperature anomalies that are created by carbon dioxide, both when glaciation is forming and when it's retreating, we can do that. And we can pop today's level up there. In other words, we are really a long way apart, a long way separate now, climate-wise, from the ice ages. We've broken free of the ice ages in a very convincing way. Temperature is tremendously important to all life on Earth. As I say, it hasn't caused great mass extinctions, but it has sure had its impact via carbon dioxide. And in that temperature curve there, we can see the late Paleocene thermal maximum. We can see the Mideocene extinctions. But the thing that I want to point out in this graph is that dive right on the right-hand side there to about -6. Now, this is the average temperature of the planet. It's not the temperature of the ice cores or any other particular place. It's the average temperature of the planet. And that -6, that dive down there, represents the ice ages. And the ice ages have had 6, 8, maybe 10 major glacial cycles. And as before, we're going to move right to the right-hand side there and look at the last 400 or so thousand years, not million years, 1,000 years. We're contracting right down. And this is the temperature not of the Earth. This is the temperature of the ice core. And there's a big, big difference. So that last interglacial didn't go up 4 degrees. It just did in the middle of Antarctica when this particular bit of ice formed. And very clever people can take this information and plot the volume of ice that existed at these various times. And when you know the volume of ice, then it's an easy calculation to calculate sea level. And so that is the sea level changes that result from the glacial cycles. And as you'll see, down on the bottom right, down here, we have the sea level plunging down to -130 meters. Now, this talk has got a lot to do with time as well as carbon dioxide. And time we must look at now, and what that means for a coral reef. That upper diagram is a reconstruction of sea level change over the same period as the bottom diagram, in other words, since the last glacial maximum to now. The area shaded pale blue is when the Great Barrier Reef would have flooded. And I'm going to make a little bit of a deal of this because it does absolutely show the enormous impact of climate on the oceans. Now, a lot of so-called climate skeptics have said, well, look at all this impact there. Today is just a bit more of it. Well, they're wrong. Am I sure they're wrong? Yes, they are definitely wrong. And it's quite, in fact, easy to prove they're wrong. But anyhow, that encourages me, though, to touch on this subject for just a little bit. And being an Australian and being proud of Australians, I am going to talk a little bit, I'm going to plug some Australians in here because they arrived in my country between 50 and 60,000 years ago. Between those red arrows, Australians arrived in Australia. Well, when they arrived, the Great Barrier Reef was not flooded. So they would have seen a very different reef. And if we move to that maximum point there, the last glacial maximum there, we can compare the modern Great Barrier Reef with the ancient one. Now, the modern Great Barrier Reef is drawn here. I live just near the Burdekin River, and I can drive a boat out a mere matter of 100 miles to the outer edge of the Great Barrier Reef. It's a very big place. But when the Aborigines first came to there, they walked out there, and they hunted kangaroos there, and there were gum trees there, and it didn't look anything like a coral reef, nor did any coral reef on this planet. And you can still see where the Burdekin Reef crosses today's coral reef. But to make this point clear, because it does, as I say, show climate change acting on the oceans, imagine you had a boat and you had a camera and you pointed it in the direction of the red arrow. That is what you might see. That is the photograph you might take. Except for the tourist boats. I think they wouldn't be there. I'm pretty sure of that one. But if you can try to wrap your mind around that, imagine that spot today, which it looks like that, and you go diving there, as I have hundreds of times. You go diving from there down that face, and you reach a place where Aborigines certainly would have walked down their pathways to go to fishing grounds. And on that pathway, they would have lived in caves. And that's a photograph inside one of these caves looking out. And all my life I've been searching for an Aboriginal burial ground in one of these caves. So keep your eye on the front page of Nature, because you'll find out that this is taking control of itself. One of these days, maybe find them. Okay, in our own era, sea level changes, very, very big things, very important things. Now, I'm going to move on to really today to mass bleaching. That is the devil of coral reefs at the moment. The impacts of coral reefs have been enormous. And mass bleaching is not a disease at all. It happens to perfectly healthy corals. And as you might know, corals have algae in their tissues, the algae, the little pitch at the top, and it's the algae that provides something like 90% of the food and oxygen that coral needs. So the coral is really dependent on the algae. And although corals are very good at catching plankton, if you cut off all light and the algae dies, the coral will die. The algae have made themselves indispensable. Well, if you raise the temperature just a little above them, what a coral really likes, you plunge it into overheating. It doesn't hurt the coral directly, but the algae love it, and they produce too much oxygen, and it's the oxygen that kills the corals. The corals have got to get rid of those tissues or die. Well, if they do get rid of the algae, they're going to die anyhow. Because this silly thing happens because literally for millions of years, corals have not had to do this. This hasn't happened. It is something that only started in the 1980s. It hasn't happened for millions of years before that. So it is something that blights corals because they're not designed to cope with the amount of oxygen produced by these high temperatures. So we might take a nice, pretty reef today with a nice lot of fish, nice little staghorn corals everywhere, and in a matter of a couple of weeks, we can turn it into that by a single pulse of overly warm water. And this has happened many, many, many times in virtually all the coral reefs of the world. That pretty white coral soon becomes that. It becomes rubble. And as you can see, not much habitat is preserved. But all is not lost. If the environment is good, if the water quality is all there, corals can come back. And they're very, very good at doing this. They're very, very good at recovering from being trashed by crown of thorn starfish, by cyclones, by anything. And they're good at recovery, being trashed by mass bleaching. Doesn't matter what the cause, they start growing back. And so that's what happens. They start growing back. So the coral reef on the left can become the coral reef on the right in a matter of a few months. And in about 10 years or so, that cycle can be returned. In other words, that rubble on the right can become a pretty-looking coral reef all over again. And that's a particular spot that I find very interesting. I took this photograph in the early 1970s. And it wasn't about a month after I took it, I found out that the crown of thorn starfish had come through and absolutely demolished this place and turned it into rubble. It grew back. It grew back to looking something like this all over again. And then it was hit by a mass bleaching event and turned back to rubble again. And it is well on its way to recovery again. This has all happened in my lifetime. I'm not all that old. And so you can see these amazing cycles showing the resilience of coral reefs if the water quality, if their environment is good. But mass bleaching is really something to behold. You really can't photograph it. You can't see it from the air. You can see it underwater if you're towed along at a high speed with sharks after you. But mass bleaching affects anything that has got zooxanthellae in their tissues, and it doesn't affect anything that hasn't. So a lot of marine life is affected by mass bleaching, but it's the corals that create the habitat that, when they bleach, that habitat becomes destroyed. And you may think that perhaps some people have said, well, mass bleaching may have been going on. It's just because a lot of scuba divers today. Well, I've been scuba diving for a lot longer than that, and I've never seen mass bleaching before 1980, and I'm sure I would have noticed it. And that is a photograph of a coral colony. It's about 600 years old. It's a very common photograph, this, because there are loads of these great big old colonies, anything up to 1,000 years, forming rows as long as a city block or more, and they're all dead. So this is something that is pretty recent. It is something that started happening in the early 1980s. So we're going to have a look at the concentration of carbon dioxide and what it's meant for the Great Barrier Reef as a representative of all reefs. And don't get too much worried about the numbers here, time and concentration of carbon dioxide, because for a coral reef it doesn't matter. That's one thing good about a coral reef. You don't have to get into details because the effects are so obvious. I'm sorry. At 320 parts per million of carbon dioxide, there's probably no harm to coral reefs in the long term. It was the concentration that was spelt the start of mass bleaching, but only in little patches here and there. It's something that a coral reef could perhaps tolerate. When the concentration came up to 350 parts per million, we got periodic mass bleaching all over the Great Barrier Reef in the Caribbean, a lot of Indian Ocean sites as well, and then at higher concentrations all over all the major coral reefs of the world. Today, at 387 parts per million carbon dioxide, we have compounding long-term degradation of the Great Barrier Reef. In other words, if you held carbon dioxide at today's level by a magic wand indefinitely, the Great Barrier Reef would gradually, slowly decline. So all its upper area to a depth of 10, 20 meters would gradually become more or less rubble. If we increase this carbon dioxide in our great global experiment we're conducting now to 400 parts per million, and we're going to do that pretty soon, it will cause major weather events. Now, I made this PowerPoint slide, I have to admit, some time ago, because last summer we had the most intense cyclone pass not far east of where I live. Went roaring down the middle of the Great Barrier Reef with wind speeds approaching 300 kilometers an hour. Now, that's a very intense cyclone. That's going to be something we're going to have to put up with a lot in the future. And 400 parts per million will cause severe bleaching, mainly during El Nino years, mainly due to the natural weather cycles that bring warm water across the warm water or warm temperature anomalies across the Indian and Pacific Oceans and cause droughts, famine, and fire. At 350 parts per million, so much toted around at Copenhagen, which will be reached, one would think, before mid-century, at about that time. It doesn't matter to a coral reef. It will cause mass bleaching most years. In other words, the ocean will have warmed up that it really doesn't need an El Nino year at all to cause mass bleaching. We go to 500 parts per million, and the average temperature of the Earth will be up perhaps 3 degrees. It will climb up to 3 degrees. And I've got there, will cause severe bleaching every year. Well, that's actually not right, because by then there won't be anything left to bleach. But if there was, it would be for it. But by then, no. Added up, there will be no shallow water corals left to bleach. At 550 parts per million, we're getting a massive temperature increase that will, in time, get up to a level that is near 6 degrees. In other words, the temperature of the whole surface of the Earth will be 6 degrees up. What does that mean? Well, think of that diagram I showed you earlier about the temperature of the Earth. That's when we had the last glacial maximum, and the temperature of the Earth went down 6 degrees. So what we're doing now, and there will be people alive here in this room that will witness this, if you don't know anything about it, is a temperature increase in the planet pretty much equivalent to the temperature decrease that we saw during the last ice age, when all of Canada was under 2 or 3 meters of ice, and most of Russia and a lot of Europe. And in fact, this country was good for skiing, I don't know, skating. You haven't got any mountains, have you? Okay. These are the devils identified here. And what I'm showing you now is the IPCC projections that are the best guide for governments that have been used to rouse awareness of climate change. And in that top diagram, we see the actual level of carbon dioxide. In other words, we are tracking, we're not tracking the worst case scenario, we're tracking well above the worst case scenario. It's worse than the worst case scenario. We are tracking the worst case scenario in temperature and in sea level change also. But sea level change, well, who's got a coin to toss? Because that's a very serious one, of course, but it is notoriously difficult to predict because there's so many wild cards in the pack, as we've seen with the Arctic ice, which the melt of 2007. A recovery since, I think, but wait till it happens again. It's unstable. And when something becomes unstable, it becomes unpredictable. As far as coral reefs are concerned, cyclones are going to be a big thing, the intensity of cyclones, and we're dealing with cyclones that we've never imagined. The El Nino cycle will become increasingly irrelevant. It'll happen, it'll still keep on going, it'll cause all the droughts, all the fires, but it will cease to be the one that's the factor that's driving mass bleaching. Thermal cap of the ocean. Now, we've always thought 31 degrees, at least as far as the Western Pacific was concerned, was as hot as the oceans could get, because above that heat went down and out, didn't warm the surface layer. But that, according to some modern calculations, is perhaps not so. In other words, it can go above 31 degrees. One hopes not. The ocean conveyor, well, the fate of the ocean conveyor is an incredibly serious thing. The ocean conveyor links the ocean basins of the world. It moves heat around the planet, so it controls a lot of our climate pattern we have today. It moves nutrients, and it also moves a huge amount of carbon dioxide, because the oceans breathe out as well as breathe in. I could rattle on about the ocean conveyor, but I'm going to make you miserable without that. One of the points of great misery that is now looming is ocean acidification. Now, that's quite a recent thing as far as marine scientists are concerned, except if you're a carbonate chemist, in which case you'd have known about it for close on half a century. When carbon dioxide dissolves in water, it forms carbonic acid, and that carbonic acid attacks the ocean buffers. In other words, the carbonates and bicarbonates of the ocean, which all carbonate, all skeletal organisms that build carbonate skeletons are used to build those skeletons. So the dissolving carbon dioxide is impacting on anything that builds a carbonate skeleton. Back to our diagram again, and this time with some predictions, clever predictions of what the world, how the world will change as aragonite changes, the dissolution of aragonite. Now, aragonite is the type of calcium carbonate that corals use to make skeletons. Where it's pale blue, everything's happy. Corals are as happy as Larry, and when it's in yellow areas, its acidification is not good. In a red area, it's bad. The reason for that is that that carbon dioxide dissolves in cold water. And so if you took a bucket of cold water from a red area, you couldn't grow a coral in, even today, even if you warmed it up. Today, that blue area is contracting. The pale blue areas are disappearing. When we reach 450 parts per million, the area that will support a coral reef is really contracting. By 500 parts per million, we've only got an equatorial band, And that fast diminishes as we get to the higher and higher concentration, until 650 parts per million, which people, some of the people in this room are likely to live to see. The map of aragonite dissolution looks like something like that. Ocean acidification is a really very, very serious thing indeed. And it's not only for corals, it's for anything that forms a carbonate skeleton. It's a big one. And we have every reason to worry about it. This is what a reef looks like when ocean acidification gets hold. They're horrible. They really are. They're very horrible places. You can reach into that and break it apart with your hands. When it gets like that, there is none of the diversity of life that a coral reef normally has. There's no starfish, there's no mollusks, there's no nothing. They're just pretty much empty, dead, slime-covered, horrible places. And if you do find a coral, it's usually got white bands around it. It's got a disease and it's dying. So it can die for a disease even if it lives through the effects of the acidification. Okay, I promised to make you happy. And so we're going to look to the future a bit. And, well, this is in case you're not happy. Or in case you are happy, and I'm going to make you even more less happy. Whatever the way. I hate giving this talk. This is the future. And the future is all about that word synergies. Everything is to do with synergies, and I'll explain. In 1980, what we had to worry about was 345 parts per million carbon dioxide. In other words, that was roughly the response of corals to an earlier time of 320 parts per million because of the ocean lag that's always imposed on these things. And it was about that level, at that time, that mass bleaching started. We didn't know what it was, we knew what caused it, we didn't even know it was a disease. We thought, oh, what's that? It's something really serious. Today, we have to worry about 387 parts per million, reefs responding to a lower level, but corals now today, bleaching will occur mostly during El Nino years, and this slide is rapidly going out of date from judging from what happened last summer. And it will be starting to, bleaching will be starting to occur in non-El Nino years. In other words, bleaching will be expected to start occurring every year from about now onwards. Synergies. Synergies 25 years from now. The synergies are a mixture of the effects of carbon dioxide, 450 parts per million, of the saturation of high magnesium calcite. That's another form of calcium carbonate. There are three main forms. The high magnesium calcite is the most soluble form, and that will be part of the synergy then. And we're going to have to worry about this increase in temperature up to about 2 degrees, and eventually, if we held it all constant at that stage, heating the Earth to perhaps over 4 degrees. Corals 25 years from now we'll be seeing mass bleaching most years, and as a result there'll be very extensive habitat destruction. And once you've got extensive habitat destruction, you must have extensive extinctions, because the organisms that live in those habitats will start to fail. As far as reefs are concerned, not just corals, the coralline algae, that's the algae that bind all the rubble of the reef together into a solid structure. They build reefs just as much as corals do. They are made of high magnesium calcite, so they are for it. They're the first major group that are really going to suffer from ocean acidification. Because of that, and because of the effects of temperature and mass bleaching, all reefs will be in stepwise decline, and we will see biodiversity reduction accordingly. And I'm not talking about a few percent, major biodiversity reduction. 50 years from now, synergies will be kicking in a different way. Carbon dioxide, aragonite, the stuff that coral skeletons are made of, will be affected by ocean acidification. Temperature will be added to it, and we'll also have sea level rise. Heaven knows how much. I've put 400 in there at a guess. It's this mixture of impacts, the synergy, the accumulated outcome of these 4 different drivers, they will ensure that no coral occurs below 10 metres, maybe 20 metres, maybe 30 metres. Calcification of anything will be marginal, it must be. And as a result, extinctions will be extensive. Reefs at this time, there'll be no reef building at this time. That'll be something of the past. You look it up in textbooks. All reefs of this planet will be highly erosional. They'll be going backwards. There'll be no shallow water habitats. That the sort of habitats where corals form the home for these fish. As soon as you take that habitat away by destroying the coral, the fish have got nowhere to live. They will go as well. The evolution of fish is very much correlated. A reef fish is very tightly correlated with the evolution of these branching corals. And there will be no coralline algae. They won't exist in an ocean acidified to this extent, and will have huge physical impacts made worse by sea level rise combined with the supercyclones. Now, we're heading for the conditions that perhaps occurred during the mid-Eocene. Now, the mid-Eocene, that's the earlier diagram I showed you, the mid-Eocene carbon dioxide levels were around about 2,000 parts per million, not the 600 parts per million that we are talking about today. So why make the comparison? Well, actually, it's a very, very valid comparison. And the reason for that is we are increasing carbon dioxide so fast, it is remaining in the surface skin of the oceans. It is not getting injected down to deep water where it can be buffered, where it can be counteracted by carbonates. The oceans can never go acidic. We've got an effectively infinite amount of carbonate down there, which will de-acidify water. But it's not getting a chance to operate today because we are increasing calcium carbonate so quickly. So that's why that's approximately, as far as a coral is concerned, a pretty realistic approximation. 75 years from now, the synergies kick in. Calcite, the third form of calcium carbonate, that's the form of calcium carbonate that most mollusks build their shells out of. Temperature way up, sea levels up, we don't know how much. Calcifying organisms, corals, will have gone altogether, or be askeletal. Now, I say this word, askeletal. Corals can actually live without skeletons. And it is one of the fantastic, the corals have got a lot of the tricks in their little bag, but this coral lived in an aquarium for over a year. He's a big guy. And he lived in an aquarium. He didn't want a skeleton. And corals, in fact, can live without skeletons. You can dissolve them away in acid waters. It completely changes their biology. It's not even known they're reproductive, but they can live. And it may be a way of some corals surviving acidification. Who knows? But they won't have anything to do with reefs. Mollusks will have to be in sharp decline, and obviously there's going to be huge biodiversity loss. 100 years from now, we needn't worry about synergies. We won't be producing the carbon dioxide. It'll be produced by a runaway, out-of-control path that the geological record has shown so often before. Corals will be extinct or askeletal. All other taxa will be going extinct. Reefs will be mostly wave-washed geological structures. And the sixth mass extinction, such as we had in KT, will be on the way. How could it not be? That is major ecological collapse of one ecosystem after another, not just coral reefs, but in the past led by coral reefs. So in summary, with carbon dioxide, 320 parts per million, occasional bleaching. 340 parts, sporadic mass bleaching. 387 today, inevitable long-term decline of coral reefs. 450, the bandied about level of Copenhagen. Rapid decline for coral reefs, and reefs cease to be biodiverse, and they will. 600 parts per million, acidification will be kicking in and affecting all biota. By 800 parts per million, as I said, the mid-Eocene extinction equivalent will be in, and 1,000 parts per million. Well, I think humans will have joined the mass extinction rally. Okay, now, I saw this young lady in a recent dive I did. I was photographing a coral, and she popped her head out, and she told me to go away, as eels do. And so I thought, well, she's got a point, because I'm really the ultimate predator for her. She's probably never seen a human before, at least where she was, and she wanted me to go away, and I did. But when I went away, I was just thinking, she doesn't really know she doesn't really know how big an ask or what the real problem was. She just wanted me to go away. She didn't realize the size of the problem that I and my kind have created for her. Now, the Great Barrier Reef and the Great Wall of China were the two structures commented on by the first astronauts as showing that the Earth had life on it. The Great Barrier Reef is very big. It's bigger than the UK, and it's more biodiverse than all of Europe. So that's what we're talking about losing in a few decades. She didn't realize that. What she also didn't realize is that once you start losing the Great Barrier Reef and the likes of it, you really have a domino effect. It'll flow onto all reefs. It'll follow onto benthic communities, marine communities in the high latitudes, which are prone to acidification. It'll affect fish. It'll affect pelagic communities. It'll affect everything. That's the domino effect. That is the path that mass extinctions take. And so what you really didn't know, that ecosystem failures are mass extinctions. And however much we want to talk about the economic problems associated with climate change, they pale, they're trivial compared to the problems that are created if we start up a runaway carbon dioxide, climate change, explosion, and go into mass extinction. 450 parts per million will bring on the demise of the Great Barrier Reef, coral reefs worldwide. No doubt about it. There's not a scary doubt about it. Just how that will flow on in a domino effect to other reefs, we don't really know. People are just looking at that now. It's scary stuff, but what that eel really needs to know is that she needs to have between 320 and 350 parts per million. Otherwise, she really is unlikely to make it. A lot more detail of what I've been saying is in this book I wrote. If you have any problems, any thoughts, you want to know more about something rather, by all means contact me. Email me at coralreefresearch.com. That's easy to get to me. If you would like to have a copy of this PowerPoint, that's the URL. If you don't want to write it down now, just send me an email and I'll give you that URL and you'll be able to download it. The views expressed in this presentation are mine. I got that off the back of a cornflakes packet just as I was making this. But what I really wanted to say is that I'm not just an ancient mariner who's spinning a tale with an eel instead of an albatross. I really have got something to say. And that saying is backed up by about 3,000 major publications that I've read to make this PowerPoint, obviously over a long period of time. Those 3,000 peer-reviewed publications represent the best science that this planet has to offer. And I, for one, am very much at home now with these 3,000 publications, and so are 1,000 colleagues that I've spoken to over many years about the various aspects of this talk, and drunk a lot of beer with other aspects of this talk. This scenario is completely backed by the Great Barrier Reef Marine Park Authority, the Australian government arm that looks after the Great Barrier Reef. The Australian reef scientists have asked me to specifically say that they're right behind what I'm saying here. And just before I got on the plane, the International Society for Reef Studies say, please put our name on this. We want to get in this too. So this talk, I'm talking on behalf of literally thousands of scientists who really are otherwise quite silent. It is also embraced by a host of major research organizations and institutions, as acknowledged in my book, and now peak science organizations who pull lots of science together as a representative of a very widely held opinion. So, ladies and gentlemen, please think of this eel Think of her problems. Think of what I've had to say. When you leave this building, please don't say, that was a miserable talk, and go and do something else. By all means, think this was a miserable talk. But please, I beg of you, think of the issues that are involved at the destruction of coral reefs. They beg belief. There's something nobody should have to stand up here and say, but it is reality. Please, some of you have got influence in this matters. Some of you have got a lot of influence. But whatever your influence, be it big or small, please, after you leave this building, please use it, talk about it, think about it, because our whole future of this planet depends on this story and stories much like it being recognized and approached as something that is reality. This is not a fairy tale. This is reality. And with that, please, thank you very much on behalf of the eel, on behalf of myself, for listening to me. Thank you.